Okay, and I'll share my screen now. Okay, so we are going to continue the iterative method of decoding the product code in this lecture. Okay, so uh, as you know, we went over this iterative scheme last time, and that is the scheme that you will be working on in this week's lab, where the product code or the rectangular parity check codes have this nice structure where you can decode row by row and then column by column. Now, you remember we have drawn certain bipartite diagrams or bipartite graphs, which are also known as Ternary graphs. It turns out that this iterative scheme can be visualized on those Ternary graphs also. And for the product code, whether you think of the iterative decoding as that row by row and column by column, or you think of it as this operating on this bipartite graph, it doesn't matter. Both are equivalent, completely equivalent. And that is this example that we will see very soon. But when we consider codes that are more powerful, and specifically we are going to go over a type of codes that is known as low density parity check codes, which are actually currently being proposed for the 5G standard. There, maybe this row by row and column by column view kind of falls short, because the LDPC codes can't be visualized as forming that nice square or rectangle, but they can still be formulated on the Tanner graph, on the bipartite graph. And so we are going to look at the iterative algorithm on the Tanner graph or the bipartite graph. Now, this may be a stretch, it may or may not be true, but ultimately what is happening, even in that row by row and column by column decoding, or more specifically in this algorithm that operates over bipartite graph, it's a lot of kind of information that is getting exchanged over the edges of the graph, over the lines that connect the two nodes of the graph. And we will actually later on look at a type of algorithm which is known as belief propagation algorithm. And that algorithm actually transmits beliefs over the connections of the bipartite graph. And as the algorithm iterates, the beliefs become more and more firm. Maybe it is sort of like what is happening in our brain. So I'll give you one example. This is a paragraph that is really messed up in terms of the spellings. Each and every word has wrong spelling, but most of you would have no difficulty in reading this paragraph. Right? If you try to read it, although spellings are wrong, you will be able to still read what it says. So as the paragraph says, according to research at Cambridge University, it doesn't matter in what order the letters in word are. The only important thing is that the first and the last letter are at the right place. The rest can be total mess, and you can still read without any problem. This may be because the human mind doesn't read every letter by itself, but it kind of reads the whole word as a whole. Basically, what is happening is that the brain looks at the first and the last letter, and from there it already forms the belief of what are the intermediate letters likely to be. And then if it sees roughly the same type of letters, then it kind of solidifies its belief. And so maybe some type of iterative approach is going on in our brains. Okay, so and that is why I said that we really don't know. It may be some type of iterative algorithm that we are going to look at now, or it may be not that. Because if I give you another example, then this particular sentence is pretty hard to read. So if you are interested, you can go to this website dictionary.com and it will give you further such examples. So now we are going to look at this Ternary graph in the context of the same 9-4 product code. Okay, and remember the parity check matrix H matrix completely specifies the code because it always conforms to this equality. If the H matrix is multiplied by a valid code word, remember this has to be an actual code word, valid code word. It has to be one of 16 code words of the product code, 9-4 product code. If you take any one of those 16 code words and you multiply by H, you are going to get total of 5 zeros. And this we had already noted earlier, but in case if you're fuzzy about it, you see all that this parity check equation does is it calculates the parities, but the product code is defined to satisfy all the parities. That is how the parity bits are added in each row and in each column. So no wonder if you add all the right bits, for example, if you add all the first 3 bits in that matrix, you are going to get a 0 because I mean, no wonder that's how the first parity bit was defined. Similarly, the second parity bit was defined also in that manner. And so if you add bit number C4, C5, and C6, no wonder you are going to get a 0. So this may seem like a fancy metric equation, but all that it is saying is that the generation of the code word follows this parity check equations. And so correspondingly, we can draw this diagram. This also we have drawn earlier. This is specifically for the 9-4 product code. And it has 5 parity bits. And so there are 5 supervisory nodes, which we are going to, from now on, we are going to call them check nodes or CNs. The reason they are called check nodes is that they check whether the parities are satisfied. If it is a valid code word that has been received, then all of this S1 to S5 will be satisfied. All of them will be 0. Basically, the decoder will be happy. But if some bits are erased or some bits are flipped, then obviously some of these parities will not be satisfied. And so these check nodes are checking whether the parities are getting satisfied or not. And then in the Ternary graph, the bipartite graph, the C1 to C9 become what are known as bit nodes or variable nodes. The reason they are called bit nodes is because we take the incoming bits and just feed them to each of these circles. So the circles are nothing but the bits. They are also called variable nodes because this is what we will be keep on varying in the iterative algorithm. If all of these parity checks are satisfied, then we will not vary any of these bit values. And then we will declare that we have received the correct code word. But when some of the parity checks are not satisfied, then we will keep on changing the values of these nodes. And that is why these bit nodes are also sometimes known as variable nodes or VNs. Okay, so these are some notations.
Hello, sir.
Yes, Vandan.
Sir, I think there is a mistake in this graph.
Okay.
Sir, C1, C2, C4, and C5 are information bits, right?
Yes.
According to square parity check, all of them should have connected twice with S1, S2, S3, S4, S5. But C4 is connected 3 times and C5 is connected only 1 time. So
Uh, Yeah, so there is something wrong maybe. Just wait.
Sir,
Okay.
the connection C4 S4 should not be there, and a connection C5 S4 should be there.
Okay, good. So just hold that thought. We are going to draw the same diagram again, and maybe the mistake here will have been resolved there. Okay. So
Okay,
very
sir.
good point. That is smart catching of the error in this diagram.
How very oh, seriously not using it ever.
Okay, so now we are going to do again this decoding using an iterative algorithm, but this is going to be done in a slightly different manner. By the way, this approach is called message passing decoder or algorithm. So each node of the graph is going to pass a message to the nodes that are connected to it. And when you do the soft decision decoding that we are going to talk about, it also is known as belief propagation algorithm. So either MP or BP. So the main algorithm is essentially simply in this steps 2 and 3. These two steps are getting iterated. They are getting repetitively implemented in the algorithm. This is called the initialization step, where we just take the incoming bits and use them as the input to the algorithm. And this is called the termination step. So this is necessary to decide when to stop iterating. Okay, so this is the main thing. Message passing from the VM to the CN, and then message passing from the CN back to the VM. Remember, we first have already loaded the VN with the incoming bits. And so now these VNs are going to start sending messages to the CNs that are connected to it. So let us consider a message from the ith VN to jth CN. And this is for the BEC channel. Okay, so we are going to do this example right now for the BEC channel. Okay, so let me draw ith VN. So I'm going to write V and I. So it's going to be a circle. And then there are going to be some CNs. Let's say CN1, CN, maybe the next CN that is connected to this VN might be CN3. And then there are some CN whose number we don't know, but we are just going to call it CNJ. And there may be some last CN. Maybe the last CN is also connected, which we are denoting as CNU. U, remember, is number of parity bricks. So all of these are connected to this VN. So we are deciding how to send the messages, the message from VNI to CNJ. So in the message passing scheme, when you are iterating, what happens is VN sends messages to CN and CN send message back to the VN. Now, we are assuming here that the algorithm has already proceeded, and by the way, yeah. So there is also going to be this actual received bit R of I. Right, this is the C of I plus maybe an eraser. So ith code word bit XORed with the possible eraser. If eraser is sorry, not XOR. XOR is for only binary symmetric channel. So I will not write a formulation for R of I, but basically R of I is exactly equal to ith code word bit C of I. Let me just write it down here. For BEC channel, R of I is equal to C of I if there is no error on the ith bit. So E of I is 0. Otherwise, it's an eraser. So maybe I'll just say X. If the ith bit has been erased, then you don't get anything. So that R of I, the received bit, is what we have already loaded on ith VN in step number 1. Right? So that is what this step number 1 is. And so if VNI is lucky, then it will not be an eraser, and it will actually be equal to the transmitted bit C of I. But if ith VN is unlucky, then it will get an eraser. And that is where the problem is. We have to try to unerase all such erased VNs. And that is where this CNs connected to VNs are going to help out. Not in the first iteration, because in the first iteration, in the initialization, only VNs have been loaded. We don't know what the CNs are because we haven't reached this step number 3 where CNs start taking values. So initially, we are going to assume that all the CNs are not sending any message. But in general, for the algorithmic description, we have to consider subsequent iterations when CNs start having values. So in that case, the way to think about it is that the CN1 will send a message to VNI, CN3 will send a message to VNI, and CNU is also going to send a message to VNI. And then looking at all of these messages and the information that it got from the channel, R of I, this VN is going to tell CNJ what it thinks its value is. Okay, now I think I may not have mentioned this. So there's something called degree of the check node. Degree of the CN. And similarly, there is something called degree of the VN of each individual VN. And degree of a node is very simple. It's degree of a node in a graph is simply equal to the number of edges connected to it. Okay. So this S1 has obviously degree 3. S2 also has degree 3. In fact, all of these have degree 3. And degree of Cn, we are going to denote it for the simplicity as d of C. And degree of the Vn, we are going to denote as d of V. D of V is different here, right? So it is 2 here, 2 here, 2. This C4 has 3 actually. C5 has only 1. C6 has 2. C7 has 1, C8 is 1, and C9 is 1. Right? So this is how DC and DV are defined. So what this algorithm says is that when V and I is sending a message to C and J, it's going to look at all the message that it received from DV minus 1 other CN. So we don't look at what C and J sent us. We look at what all the other CNs are telling us. And therefore we look at DV minus 1 messages. Now, what this if statement is saying is that if all of them are erased, so this CN says that, I think you are erased. The CN3 also tells VNI that to me also you are erased. And the CNU also tells VNI that I also believe that you are erased. And even the channel is saying that VNI, you are erased. In that case, VNI will tell CNJ that I am erased. So it will send an X to CNJ. But if any one of them is not erased, then it will send the value of that non-erased message. So initially, if Ri itself is not erased, then in all the subsequent iteration, VNI is going to just send the value of Ri to CNJ. But interestingly, what will happen is that suppose VNI is erased initially. So Ri is erased. Maybe after the third iteration, the CN1, CN3, CNU will tell VNI that, you are erased. And so VNI will still tell CNJ that, in first iteration, I told you I'm erased. Even after the third iteration, I don't have anything better to tell you. I'm still erased. But it may happen that subsequently, maybe on, I don't know, fifth iteration or seventh iteration, one of the CNs will suddenly get the value of VNI. And so maybe CN1 will also still say that you are erased, but CN3 will say that your value is 1. And CNU may also say that you are erased. But as soon as CN3 said that you are 1, VNI will tell CNJ that I am 1. And one nice thing about the eraser code is that later on, suppose even CNU tells VNI that you are not erased, the value that it will send to VNI will be same as the value that CN3 would have sent. That part is guaranteed. For BEC only. And so there is no confusion at VNI. All the non-erased values that it is getting from DV minus 1 CNs, they are all going to be identical. And so it will just send that value to CNJ. Right? So this is the main algorithm that has to be implemented at each of the VNs. And each of the VN will vary this J. So first time J will be 1. In that case, VNI will listen to the messages that it got from 3, J, and U. And then using the same approach that we have mentioned here, it will send the value to CN1. Then it will go to 3, and that that time it will get the message from 1, J, and U. And then it will send this upward arrow to CN3. And so on. Now, this is how the messages get passed from each VN to each of the CNs that are connected to. What about the messages that are passed from oh, okay, yeah. So this is still the messages from VN to CN. This note I have written just to say that this type of scheme holds only for the subsequent iteration. For the very first iteration, the VN simply sends to the CN the value that it got. Okay, so this I already mentioned. Now let us look at the messages that are passed from jth CN back to ith VN. So I'm going to draw jth CNJ here, which is in this rectangle. And let us say that CNJ is connected to VN number 3, VN number 9. Then comes VNI, maybe I is 17 or something. And maybe it is connected to the last VN, the very last VN. What should be the index of the last VN?
It's N.
Yes, capital N or small n. Okay, so now what we are considering is how CNJ will send the message to ith VN. And remember again, I will, for CNJ, I will be initially 3. After it sends message to 3, it will go to 9, it will go to I, and then it will go to N. So basically CNJ passes messages to all of the VNs that are connected to it. Right now, we are just looking at how it does for ith VN. Then that, obviously can be generalized to all the other VNs that are connected to it. They're just like what we saw on the previous example. Now this part is going to have arrows which are going upward on the VN to CN direction. So these are the edges. And so let's see. So CNJ will first listen to VN3. Then it will listen to VN9. And then it will listen to VNN. So it is listening to what all these other VNs are telling to this CNJ. And then on the basis of that, it is going to send a message to VNI. Now remember, this CNJ is nothing but the single parity check code. That is what this diagram says. So the algorithm that CNJ has to do is very simple. It is the algorithm of the decoding of SPC code that we have already looked at. Now, when this 3, 9, and N, none of them are erased, right? So I'm first looking at this otherwise part, okay? So none of these DC -1 nodes are erased. Then CNJ is going to say to VNI that you are obviously modulo to some of all these green messages that I'm getting, because That is how the space is defined. So in this otherwise part, this Cnj is going to just send the modulo to sum of Vn3, Vn9, and Vnn to Vni. However, if suppose Vn3 is erased, then Cnj is in trouble because it can't do modulo to sum of something which has been erased. And so in that case, it will tell Vni that I don't know what your value is, so I'm just simply going to tell you that you are erased. And that holds for any one of this Vn3, Vn9, or Vnn. If any one of them are erased, then Cnj is going to tell to Vni that I don't know. To me, you seem to be erased. But if all of them are not erased, which may happen right away at the very iteration number 3, or it may happen later on in the iterative approach. If none of this DC minus 1 messages, remember DC is the degree of check node. Why DC minus 1? Because we are looking at all the messages that Cnj is hearing from the VNs that are connected to it, except VNI. When Cnj is telling VNI what its value is, it should not look at the message that VNI has sent itself, because then it will be kind of diluting the information that is being exchanged. The analogy can be thought of as passing of some rumor. So if suppose your friend tells you some rumor, and then after a day or 2 days, you tell the friend that, you know, I have heard that a meteor is going to strike the earth a month later. Now, when you tell that information to your friend, if that information is same as what you already received from that friend, then that friend is not getting any new information. But suppose if you have 10 other friends, and if all 10 of them have also told you that a meteor is going to strike the earth next month, and then by looking at what those 10 other friends told you, you tell this friend, the 11th friend, that yes, a meteor is going to strike the earth next month, then now this 11th friend, your actual original friend, is going to get significant information, because you are telling him or her what you heard from the others, not him. And so the information that you are sending back to that friend is kind of independent information. It is not kind of correlated or dependent information. Dependent information doesn't serve any purpose. So that is why we are always going to look at DC minus 1 messages that are received at the CN from all the VNs except VNI. So this is the node that I already mentioned, that either from VN to CN or CN to VN, when we send a message to a particular node, that message is never dependent on what that node has already informed to the sending node. Okay, so we will later on see that this algorithm can be thought of as the belief propagation, or message passing can be thought of as flow of a river in some sense, okay, very, very loose manner. And for the river to flow in a nice manner, the water flow should be kind of coming from the new directions. There are some parts of the river where the water flows in circle. There is no new water flow coming in, and this water is never going back and merging with the actual river flow. And so this water which kind of gets separated out in some sense from the main river flow, and it kind of this circle around on its own, that then tends to become kind of a diluted part of the river. There you will see a lot of dirt and a lot of maybe insects flying and all that. So that is what we want to avoid. And that is why we always do the message passing in the manner which is mentioned over here. Okay, so now let us look at the example that we had. I think this is the same diagram as before. So let us see. So this CN is correct. This CN is also correct. This CN is correct. And then CN4. Yeah, so CN4 is messed up, right? CN4 no, CN4 is right also. So Vandan, is this diagram correct, or you think there is still some error in this diagram?
Sir, your diagram was correct. I also got same as you.
Oh, okay, fine. All right. So now let us go by this diagram. This is the Ternary graph or bipartite graph of 9-4 product code. And this is, we are going to look at the algorithm operating over BEC. And so out of 9 bits, bit number 1, 2, bit number 5, and then 8 and 9 are erased. So you will recall that this is exactly the same as what we did before the break. This is the same example. But now this example we are doing using this iterative approach. Instead of doing row by row and column by column, we are doing iterations over this bipartite graph. But otherwise, it is the same exact example that I had shown you before the break. Remember, there are also 5 bits out of 9 were erased. It's exactly those 5 bits which I have put here as erased also. Okay, so that part is fine. And what I'm showing here is step 1, where we are just loading the VNs by the values that we got over the BEC. And so these are the values we got. Wherever we got eraser, we just put X or E or -100 or whichever symbol that you want to use. It cannot be 1 or 0. Other than that, you can use any other symbol to denote that that particular VN is erased. Okay, so now we are going to do not maybe a full kind of diagram of this iterative algorithm, because then I'll have to go over many slides, but maybe some key parts of it. Okay, so we're going to directly jump to this CN, CN2. Why? Because for CN1, nothing, it's not going to be interesting. For CN1 is connected to 2 erasers, and so it can't do much. So CN1 we are not looking at, but CN2 is more interesting. For CN1, in this step number 2, these 2 VNs are going to pass a message, and they are going to say that I am 1. So that is VN to CN message passing, right? That we looked at. then Cn to Vn message passing for this particular Vn, which was, remember, it was erased earlier. Because both the nodes connected to this Cns are unerased, this Cn will be able to tell this Vn that, you know, I have figured out what your value is. You can set yourself to be 1. This is the simple parity check equation. So if that earlier description of how the messages are passed was confusing to you, this is how it is done. Very simple. Let us look at one more example. So remember, even the first bit was erased. So when we go to Cn number 3, Cn3 would have received messages of 1 and 0 from these two other Vns that are connected to it. And so it will tell the first Vn that you are 1. So the first Vn will now be unerased. One thing that I want to mention is that this Cn is, what is the message that it will send to this this Vn? Remember, it is going Vn by Vn. So I have drawn the message that it sends to this Vn, Vn number 5. But before it went to Vn5, it would have sent some message to Vn4. What do you think that message would be?
Zero, sir.
It couldn't figure out what its value is.
Correct. It cannot figure out what its value is. Why is that? Because when passing a message to that Vn, it would have to look at the message that it got from these two Cns. But out of these two messages, one is an eraser. So it doesn't know how to do SPC. So surprisingly, it will send to this Vn4 a message that you are erased. But it is not going to have any effect on the algorithm, because remember, from Vn to Cn, even if one of dv minus 1 or the received value is not an eraser, the Vn already knows what its value is. So even though over here, this Cn in the first iteration sends a message to Vn4 that you are erased, Vn1 is not worried, because it already knows that its value is 1. So it is just going to ignore this E. Same thing when Cn2 sends a message to Vn number 6, it is also going to send an eraser, because there's going to be this E here. But again, Vn6 already knows what its value is, and so it's going to ignore. Okay, so the same scheme is shown here for another example where the Cn3 is going to be able to unerase Vn1. Why? Because the other two Cns that are connected to it, they both are not erased. Okay. Then it's going to unerase this last parity check bit also, this Cn number 5. And so that is going to be the end of iteration 1. Now in iteration 2, the second Vn is also going to get unerased, because the first Vn got unerased in the previous iteration. And then similarly, this algorithm will keep on going from Cn1 to Cn2 to Cn3. Nothing will change there, because all the connected Cns are already unerased. But when it goes to CN4, that CN is going to be able to unerase the last bit that was still erased. Okay, so that is in nutshell the iterative algorithm. Very important that you note that I didn't describe how the message passing is happening from each VN to each CN for all the iterations. I just took some selected examples. For example, as I said already, I didn't draw this diagram. But when you implement the algorithm in MATLAB, and by the way, this is going to be your final project where you will implement this message passing algorithm on a Ternary graph. Your algorithm will actually have to do everything. Okay, so when the algorithm goes to CN1, it will have to pass message to VN1, VN2, and VN3. Although we can see right away that the message it will pass to VN1 will be erased because this node is erased. But your algorithm can't see this type of diagram, so it will still have to do that part. Okay, so that is what the algorithm has to do. Basically, these are the two main steps. Step number 2, where ith VN sends a message to jth CN. And these I and J are the variable. So, I mean, they take all the values. So you go to first VN, so you set I equal to 1. And then you change the value of J from 1 to DC. Remember, DC is the, 1 to DV. DV is the degree of the variable node. So basically you go to each of the CNs, DV CNs that are connected to that first VN. And you use this algorithm to send the message. Then you increment I, you make I equal to 2, and then again repeat the same thing. So that is going to be the main part of your algorithm. And this you will do in the context of the LDPC codes, the 5G codes. So those of you who do a very good job in this project, I want to emphasize that you will be doing something very amazing. In the first year of your BTech, you would be doing what engineers in the industries all over the world are trying to figure out how to do, which is the decoding of the 5G LDPC code, the 5th generation cellular system LDPC codes. You would have done that algorithm. So it should give you a solid boost in the confidence, and I think it will look very good on your resume also. Okay. So now let us do a few other things. So this, these two steps that I have mentioned, they are for the BEC channel that I already mentioned. Okay, now I'm going to ask you let us now define the message passing step 2, same step as before. for not the BEC, but for the binary symmetric channel, BSC, instead of BEC, binary symmetric channel. So binary symmetric channel doesn't have erasers, right? It has flips, bit flips. So how will this step number 2 change? Maybe this diagram you can see. It might help you figure out how should I calculate the message that is sent upward from ith VN to jth CN, given that ith VN has heard messages from 1, 3, U and R of I. Any idea?
Sir, is it on the basis of number of same input?
Number of the same input. What do you mean by that, Harsh?
So, like we used to check for how many bits are flipped in a message. So, if we get more number of
But you
one,
don't, no, wait a second. You don't know which bits are flipped in the BSC case, right? If you knew that, you would just unflip those bits and you are done. Okay, I'll ask you to think like this. Suppose there are no errors in the received uh, sequence. So all the VN, VN1, VN2 up to VNN, they are actually the transmitted code word bits. And now suppose even though they are transmitted code word bits and each of the CNs are going to be all satisfied, they are all going to be happy. I just want you to imagine in that case, suppose even if we did this algorithm iteration, what will be the value that CN1, CN3 and the CNU will be sending to VNI in this ideal case when there are no bit flips?
Its own value.
Yes, right? I mean, this is the ideal case. There are no errors. And so all of the CNs will be sending the same bit to VNI. And that value will be same as R of I, because even R of I is not in error. So in the ideal case, can you think of how you can represent this VNI?
XOR of C1, CN1, 3 and U.
It's not XOR. Okay, fine. Let me put it this way.
Intersection.
What is CNJ? This square that we have drawn, it's a type of code that we have already studied. What type of code is this CNJ?
PC code.
Summation of all VN modulo 2.
Who said SPC code?
Push.
Yeah, Kush, you are correct. Yeah, CNJ is the SPC code. I mean, that is how we have defined this diagram in the first place. Each of the CN is basically making sure that the corresponding VNs have even parity. They have even number of ones and even number of zeros. It's an SPC code. So likewise, I'm asking you to tell me what type of code is VNI? And Vandan already gave the hint that in the ideal case, all of the CN1, CN3, CNU are going to send. Sorry? Can you say again?
Repetition code.
Exactly. So VNs are repetition codes because they are expecting to hear their own value from all the connected CNs. Their own value should be received on all of these edges as well as from the channel. So I'll say here that each CN is an SPC code. And likewise, think of each VN also as a code. In fact, it's nothing but the repetition code. Okay, so for the BSC, what does the repetition decoder do? Remember, in case of BSC, VNs is never going to hear that it is erased. It is always going to get zeros and ones from the CNs as well as RO5.
Majority voting.
It's to take
Exactly.
boundary condition.
Exactly. So, therefore, the message sent by VNI to CNJ is equal to majority vote decoding vote of majority vote of what?
All
Other CI.
Majority vote of BV minus 1 CN messages and RO5. Yes, makes sense?
yes, sir.
In fact, it's kind of, in fact, maybe simpler than BEC. For BEC, you have to check, okay, are all of them erasers? Yeah, then I have to send erase. If not, then I will send the value of non-erased message. So there is some if-else statement that you have to implement in your program. Here, there is no if-else statement. All you do is just majority vote. So maybe instead of writing 3 lines of code, if, well, no, 5 lines, right? If, then the program for the if case, else, and then the program for the else case. So instead of writing those many lines, this part is simple. It's just 1 line of code. You do just majority voting. And then now let's go to this part. For the BEC, the message from CNJ to VNI is equal to what? This is very simple, guys. The CN is, you know what type of code it is.
Eraser if any one of is eraser.
Oh, sorry. I'm my mistake. For BEC, we have already done it before. So this should be BS. I'm asking you to tell me this step that we have done for the BEC channel, how does it modify for the BS binary symmetric channel? The answer is actually very simple.
It will be same.
Huh?
It will be same as in BEC that summation of BC minus 1 VNs mod 2.
But in BEC, you have this problem that you might see an eraser, and so you can't do summation of BC minus 1 values. So I think your answer is correct, except again, this if part is not needed. The CN is a SPC code, and so it will just do SPC decoding of BC minus 1 values or VN messages, I should say, to be consistent. Which is nothing but XOR of, in this case, if you just take that example, VN3, VN9, and VNN. XOR of VN3, VN9, and VNN, capital N. Okay. For the example on the previous slide. So again, I think decoding actually becomes a bit simpler. You don't need, again, this if condition. Okay, then the last thing that I want to mention about this iterative algorithms is that, okay, we will go to this observation later on. But what I want to mention is this hard versus soft decision decoding. So what we have done so far, it is known as hard decision decoding. And as a conceptual algorithm, it is a good algorithm. And when the LDPC codes were first defined, several hard decision decoding algorithms were developed. And then in addition, one soft decision decoding was also defined. Now, as the name implies, you can guess that soft decision is probably going to be better than the hard decision. So let us see how this hard decision that we have looked at earlier, what it is and how it differs from the soft decision and why soft decision is better. And so now, actually, we are going to look at a very simple example. It's just RAID 1/5 repetition code. It's not product code. It's not any of these other codes that we have seen on bipartite graph. Just consider RAID 1/5 repetition code that we have studied earlier. And let us assume that this code is sent over BPSK channel. I mean, using BPSK modulation over a Gaussian noise channel. So we know that for the BPSK or the antipodal case, 1 gets converted to 1 volt and 0 gets converted to minus 1 volt. Or that 1 volt can be 5 volt or 10 volt. The exact value doesn't matter. Again, what matters is the received voltage compared to the noise voltage, or in terms of powers, received power over the noise power. So the exit value doesn't matter, but so and therefore, for the sake of simplicity, we'll just say that 1 is sent using 1 volt, 0 is sent using minus 1 volt. And now suppose that this code word is because repetition, this 5 ones are sent. And they all will be sent as 1 volt, 1 volt, 1 volt 5 times. But the receiver, because of the noise, it ends up saying 1.1, 0.9, and then the other 3 values are pretty close to 0. Okay, so let us consider this example. And so what will the hard decision decoding do? It will actually convert each of this into hard decision. It will make this to be 1, 1, and then minus 1, minus 1, minus 1. And so it will get this as the output. The hard decision decoder will get this, will actually see this value that is being received. And now it will perform the majority word decoding. And so it will say that bit 0 was transmitted because zeros are in majority. Now, look at this example here that I gave you. And in case of hard decision decoding, it, as we saw, it made an error. Is this error avoidable? Can we do something better at the repetition decoder? And to answer, before you answer that question, what I want to ask is that what is the decision boundary of BPSK demodulator?
0.
Right. We have seen that earlier, that BPSK demodulator compares each bit against 0. And if the value, the voltage received is positive, it will say that 1 is received. If it is negative, it will say minus 1 is received. And so that is how it ended up decoding this. The demodulator ended up decoding that as 11000. First 2 are positive, the rest 3 are negative. Now, the other question is that suppose if the received voltage is exactly at the decision boundary, it's like ending right on the top of decision boundary, maybe R is exactly 0. Then what happens to the posterior likelihood ratio?
Becomes 1.
Equal.
It becomes 1, or both x equal to 1 and x equal to 0, they become equally probable. When posterior likelihood ratio or the odds are exactly 1, that is when the receiver has the least information about what the transmitter sent. On the other hand, when the posterior ratio either is very high, which will be the case for 1.1 and 0.9, or it is very low, which would happen if instead of this being minus 0.01, if it was minus 10. In those cases, the receiver knows with a very strong confidence, basically the belief is very high at the receiver that the transmitted bit is what it has demodulated. But if the R value is very close to the boundary, the receiver has pretty much no knowledge. And so when the receiver gave this output, the demodulator generated this output, these 2 values are actually arrived at with a lot of strong confidence. Whereas these 3 zeros are pretty weak zeros because they are very close to the decision boundary. And so maybe a better thing for the demodulator to do would have been to say that actually, I don't even know what these three values are. Because my likelihood ratio is very close to 1. And so I can't decide. Whereas the first two, I'm very sure that they are both 1. And so if you even simply ignore these last three values and decide only based on the first two because they are strong, then actually you will end up making the right decision. But even more specifically or more significantly, the reason why the soft decision decoding actually is the right algorithm is because, like what we already saw, it actually looks at the likelihood ratios. And so it, in fact, is the Bayesian algorithm. Whereas the hard decision decoding is kind of ad hoc. It doesn't have any Bayesian principle running underneath it. So soft decision decoding is going to be better than hard decision decoding. And soft decision decoding is going to give you kind of sort of an implementation of the Bayesian algorithm. And when you do soft decision decoding, on those edges of the Ternary graph, instead of passing ones and zeros, you would be passing the likelihood ratios, which are nothing but your beliefs about what the values are. And so therefore they are called belief propagation algorithm. So the message passing implemented for soft decision decoding is called the Bayesian belief propagation. Okay, so that is the important advancement of the decoding algorithm. So tomorrow at 11:30 when we meet, I'm going to go over the same CN to VN and VN to CN algorithm. But now we are going to actually, instead of passing bits as messages, we are going to pass the beliefs. So there's two slides that we did, right? This slide here, and then same way this slide. We are going to add similar two more slides for the soft decision decoding or Bayesian decoding. And so with that, once we define that, then our topic of iterative decoding is going to be over. Then we'll look at how LDPC codes are defined. And once, that is just the definition of LDPC codes. From that point onward, you should be able to start your project work on implementing both the hard decision decoder and soft decision decoder for the LDPC codes. Okay, so I'm going to stop here and I'm going to